So today we're going to take a look at example 1-18, which is a multi-component steady-state gaseous diffusion problem with a chemical reaction. And the reaction that we're going to look at is the decomposition of ethanol to acetaldehyde and hydrogen gas. We'll look at the individual components, so component 1 will be our ethanol, component 2 will be our acetaldehyde, and component 3 will be our hydrogen gas. And we are looking at this reaction inside of a Stefan tube from Z equals 1 to delta. And the initial conditions of the problem we're given are that the mole fraction of component 1 is 0.6, the mole fraction of component 2 is 0.2, and the mole fraction of component 3 is also 0.2. We're given that the first order rate constant for a reaction is 10 moles per meter squared times seconds, and our delta, or our film thickness, is 1 millimeter. Our temperature is 548 degrees Kelvin. Our pressure is 101.3 kilopascals. We're given the diffusivity coefficients in respect to each component. So the diffusivity of 1,2 is 72 millimeters squared per second. Diffusivity coefficient of 1,3 is 230 millimeters squared per second. And diffusivity coefficient of 2,3 is 230 millimeters squared per second. We are also given that the molar diffusion flux for component 1 is equal to the rate constant K times Y1 delta. So that's our composition, our mole fraction of component 1 at our Z equals delta. And then that the molar diffusion flux of component 2 and component 3 is equal to the negative molar diffusion flux of component 1. And we also know that the mole fraction of component 3 is equal to 1 minus the mole fraction of component 1 minus the mole fraction of component 2. And we are ultimately being asked, what is the overall rate of reaction at steady state? So we're ultimately going to have to try and find our mole fraction of component 1 and component 2 at delta, and the molar diffusion flux for component 1. So what we're going to go ahead and get started looking at is our Stefan-Maxwell equations, and we're going to scale those to this problem. So we know initially that our Stefan-Maxwell equation is dyi over dz, so the change in mole fraction over the change in position, which is our driving force, is equal to the summation from j equals 1 to n of the mole fraction of component I times the molar diffusion flux of j minus the mole fraction of j times the molar diffusion flux of I divided by our concentration times the diffusivity coefficient of ij. And since we are only really trying to find our mole fractions of component 1 and component 2 at our delta, we can make our Stefan-Maxwell equation in terms of each of those two components, and we don't have to worry about component 3. So then we have dy1 over dz, our driving force for component 1, is equal to y1 n2 minus y2 n1 divided by concentration times diffusivity coefficient of 1, 2 plus y1 n3 minus y3 n1 over the concentration times the diffusivity coefficient of 1, 3. So we're comparing component 1 to component 2, and we're comparing it to component 3. And then we do the same thing for component 2, where we're comparing component 2 to component 1, and we're comparing component 2 to component 3. Now that we have our Stefan-Maxwell equations for both component 1 and component 2, we can actually make this a little bit easier on us, make it a little bit simpler by instituting the variable eta, which is represented by this kind of curly n here, which is equal to our position over our delta, or our film thickness, or our boundary layer, if you want to call it. Now we use this eta because its definition is it's a ratio of the position of the film thickness, delta, a ratio of the position to the film thickness, or the boundary layer. So it's going to be some value between 0 and 1, since you can kind of assume that our z starts at 0, our position starts at 0, and it goes to delta. So you can kind of assume that the max value will always be delta for our position z, so that means our max value for eta would always be 1. And using this, it gives us a better understanding of the position through the reaction, as far as comparing it to the thickness of the film, or the boundary layer, since we're incorporating our delta value. So we can go ahead and substitute our eta in. So then we'll eventually have, now our new driving force is dy1 over d eta equals delta over the concentration times diffusivity coefficient of 1, 2 times y1 n2 minus y2 n1 plus delta over the concentration times diffusivity coefficient of 1, 3 times the quantity of y1 times n3 minus y3 n1. And then the same thing goes for our component 2 as well when we substitute in eta. Next, we have to take from the information that we do know and make some order of magnitude estimates for our unknown variables. So what we can do is we can look at these variables here, so our delta divided by our concentration times diffusion coefficient, and make an estimate based off of these values. So we know that the concentration is equal to the pressure divided by RT. So we can substitute that in for C, since we're given all 3 of these values. And then when we're making our estimates, we can assume that our delta, our film thickness, is equal to 1. And then we divide that by, again, our pressure we'll estimate it to be 1 times 10 to the 5th. And then our R we'll estimate to be 10 to the 1. And then our temperature we'll estimate to be 10 to the 2. These are, again, just based off the physical number of digits in the values. And then we'll multiply this quantity by 10 to the negative 5th, which is the diffusivity coefficient estimate for gases. Again, that's 10 to the negative 5th. That's approximately 10 to the 3rd. And then if we assume that our driving force is equal to 1, then we can apply our estimate from this quantity here and eventually get our initial guess that we'll put in for our delta to be 10 to the negative 3rd. So now what we can do is use the information that we have and use Python to help us solve for the overall reaction rate of the reaction at steady state. So now we'll move on to the Python section of the problem. So first things first, we're going to import all of our Python function packages. So we're going to specifically use the solve IVP That's to help us with our initial value problem, as well as the root function. So the first thing that we're going to do is look at our preliminary calculations. So we're first going to define our initial values. So again, these values were given to us in the problem. So we have our temperature, our pressure, our delta, which is our film thickness, our initial mole fraction for component 1, 2, and 3, and then our diffusivity coefficients for 1, 2, 1, 3, and 2, 3, as well as our R value, our reaction rate constant, which is 10, and then simplifying our concentration value, and then also our Y1 delta guess, which I'm going to use 0.001, which we found from the first part of the problem, our order of magnitude estimate. Next, we're going to define our dy corresponding to our Stefan-Maxwell equations. So our dy's in terms of eta, our mole fraction, and our mole fraction of component 1 at our delta or our film thickness. And we know that N1, again, is equal to our rate constant times the mole fraction of component 1 at our delta, and then our N2 and N3 are equal to the negative molar diffusion flux of component 1. And then here we have our actual our Stefan-Maxwell equations for D1 and D2 that we found initially when scaling these. The next thing that we're going to do is look at how the mole fraction changes with change in position through our diffusion path or our film. We're going to use our function for our initial value problem. So we're going to look at defining what our change in mole fraction is as we move along the diffusion path or the axis of the zeta delta. So we'll look at our values of dy from 0 to 1. We're going to be integrating from 0 to 1 with respect to initial values of the mole fraction of component 1 and the mole fraction of component 2. The next thing that we're going to do is look at optimizing our root. So we're basically going to find where our mole fraction of component 1 and component 2 are equal to 0. That way we can calculate molar flux. So again, that's going to be from, we're looking at solving the initial value from 0 to 1 with respect to our variable for a change in mole fractions. And next we're going to look at essentially how the mole fraction of component 1 and component 2 change with position in regards to eta, and remembering that eta is a ratio of the position to the thickness between 0 and 1. So we're estimating eta from 0 to 1. And basically what this is saying is we're going to look at eta again from 0 to 1, and we're going to look at 11 different points between that. So these two lines of code here, our Y1 and Y2, are essentially showing our changes in our mole fraction of component 1 and component 2 from eta, from when eta goes from 0 to 1. And then this line here is just showing you an array. So this is showing you the 11 different points that we were using across this. So it's showing the change in mole fraction of component 1 and component 2. So you can see that starts at 0.6 for component 1, 0.2, and then as the reaction proceeds, or the ethanol begins to decompose, you can see that essentially the mole fraction of ethanol decreases over the change in position, while the change in the mole fraction for acetaldehyde here increases as the reaction progresses and changes in position. Then the next thing that we're going to do is we're going to actually go ahead and plot these values. This code here is just essentially to make our plot down here. So what this is showing is as we move through our position of Z, you can see that the mole fraction, how the mole fractions for each component changes. So like the mole fraction for component 1 decreases steadily as the reaction continues, and then the mole fraction for the other two components increase as the reaction progresses. Lastly, we'll go ahead and actually show again what the overall rate of reaction at steady state is. So that's what this code is doing here, and the printout here actually shows our final values. So our overall rate of reaction steady state is 0.8878, and then I've also shown what the mole fractions of each component is when the reaction is at steady state.